Okay, we're going to cover section 5.4. This is all about fundamental theorem of calculus part 2. So the first thing they're going to talk to us about something called an area function. And what we're going to do with this function, we're going to denote it a of x. And we're going to start the area function at a, and we're going to set the variable to the upper limit x. And since I'm using x for the upper limit, the function that I'm taking the integration of, I have to switch its variable over to t, because, or a different variable, could use something other than t, but x basically is being used for the function limit, or sorry, not the function limit, the upper limit of the integration. So I can't use it for the variable in my formula here. What this will equal the signed area from a up to x. So for a picture basically of what that's going to look like is, suppose we had a curve and a is here, and suppose we chose x out there. What we're finding is the area under the curve from a up to x. So this bit of area right here is what it is that we're trying to figure out. It's going to be the signed area. So if this part dipped below the x-axis, say we had something like this, and a maybe is here and x is out here, this part of the area would be positive, so that would add to the value. This part of the area we would kind of consider it like negative area, so this would cancel out that part. So it's the signed area from a to x. So we're going to do a couple quick examples. In this part right here, we're going to do all the book examples, which should be enough to do the homework. But this stuff turns up a little bit different on the AP test. So what we'll do is the second part of these notes will be just working some old AP test problems that involve this. So let's see here. For example 1, they give us the area function a of x is equal to the integral from 3 up to x of t squared dt. They want us to find an equation for a of x. So find formula for a of x. So basically what I need to do is evaluate this derivative, and when I evaluate the derivative, that should give me...
Teachers, pardon the interruption. It's time for the Lucky Duck drawing, and today's Lucky Duck is duck number 43. Come on down to 203 to claim your prize. You guys have a great weekend.
Okay, so we're going to say, all right, t squared is what we're dealing with here. The antiderivative of t squared is 1/3 t cubed. We're going to evaluate this from 3 up to x. We're going to be using the fundamental theorem of calculus part 1, which says it'll be 1/3 with the upper limit replacing the variable minus 1/3 with the lower limit replacing the variable. 3 cubes 27, so I guess let's write it out this way. A of x, so a of x here is equal to 1/3 x cubed. This is really 27. 27 divided by 3 is 9, so it's 1/3 x cubed minus 9. And this will be our area formula. Okay, so we got our area formula back from that. And we can note the derivative of this does go back to x squared, which is the same form. Note, we would say if we did a prime of x, that would equal 1/3 times 3x squared, and then minus 9 would just go to minus 0. 1/3 and 3 cancel, so this a prime of x, this would just equal x squared. So it's kind of a little side note. If we take the derivative of this, we get x squared, which is the same form as t squared that we have here. So if we take, if we have one of these area formulas and we take their derivative, we get the interior, the integrand here back, but the x variable replaces the t, basically, or whatever variable used for the upper limit replaces the other one. So we're going to write down fundamental theorem of calculus part 2, and then apply it. And we abbreviate that FTC2 is okay. So we'll say assume that f of x is continuous on an open interval I and let A be an element of I. Then the area function we'll call it A of x, which equals integral of A up to x of f of t dt. So this area function here, and that's an important equation, so they're going to box it in, is an antiderivative of f of x on I. So we could say that is A prime of x is going to equal f of x. And we could also state, so they say equivalently, if we took the derivative of the area function this will equal f of x. Also, the area function evaluated at a, that equals 0, because the integral from a up to a is nothing. So we kind of saw this here. Whenever we took, we got our area function here. When we took the derivative of it, we got back x squared. So it was the same form that we had in here, but we had x squared instead. So that's kind of what they're saying here is if you take the derivative of, the area function, which you have a up to x of f of t dt, you get the f of t format, but instead of t for the variable, x becomes the variable. Okay, so that is our fundamental theorem of calculus part 2. We're going to do a couple examples from the book to kind of see what this gives us. And then that'll be enough for y'all to do the homework. And then on the in the part 2 of this video, we'll put a couple examples, or record a couple examples of what this looks like on the AP test. So, all right, for this example here, example 2 from the book, we're going to let f of x be the particular antiderivative of f of x equals sine of x squared, satisfying that f of negative square root of pi is 0. We want to express capital F of x as an integral. Okay, so what we're going to use a couple things here. Up here, they say that this area function is an antiderivative of f of x on I. So they're wanting us to, f of x is an antiderivative of little f of x equals sine of x. So we need to construct an area function based off of that. And then we're going to use that the area function evaluated at a, the lower limit, is 0. And that's going to let us get this initial condition here. So basically what we're saying is, if we look at the integral from, we'll figure out the lower limit, but it's going to be a limit up to x of sine of t squared sine of t squared dt. This right here, this will have the right format. Since I want f of negative pi to equal 0, I need to set the lower limit here to be negative square root of pi. And then this is basically our integral. This will be the capital F of x. This is an antiderivative because if I took the derivative of this would be our answer. Say note f prime of x. Well, if we read up here what happens when you do a prime of x, you get the integral format, but instead of t you get x as a variable. So if we did f prime of x, we would get sine of x squared back. So this right here is an antiderivative of f of x equals sine of x squared, because when I take the derivative of the function f, I get sine of x squared back. And also, if I wanted to figure out what's f of negative square root of pi, that would equal negative square root of pi. We would be evaluating by plugging x in with negative square root of pi, sine of t squared dt. And since your lower limit and your upper limit of this integration are the same number, this integral doesn't give you any area back. It gives you 0 back. So we can check from this format the antiderivative. It's doing the correct things as an antiderivative, so when I take its derivative, it goes back to sine of x squared. And it also satisfies this initial condition here, or this condition here that the function evaluated at negative square root of pi is 0. So if they give you a expression like this and they want you to generate an antiderivative satisfying f of something equals 0, you could think about using the fundamental theorem of calculus part 2 and kind of note that the area function is an antiderivative of f of x on I. So that is something to kind of think about. All right, this next one's going to be a little strange. So we have this area function a of x equals the integral from 2 up to x of square root of 1 plus t cubed dt, and they want us to find the derivative. And then they want us to also calculate the area prime function, so the derivative of the area function evaluated at 2, the derivative of the area function evaluated at 3, and then the area function itself at 2. So if we want to get a prime of x, it's asking us to take d dx of the integral from 2 up to x of square root of 1 plus t cubed dt. And if we do that, if you take the derivative of the integral in this format, saw here, if you take the derivative d dx of integral of a up to x of f of t dt, you get the f of t, but with x replacing the t. You get the integrand back with the variable x, replacing the t's. So our integrand is square root of 1 plus t cubed. So we'll get square root of 1 plus x cubed. And that'll be our area function. So we found the derivative, or that'd be the derivative of the area function that we were trying to calculate. So we found a prime. Now I need what's a prime of 2. What's a prime of 3? So a prime of 2, we replace x with 2. This will be square root of 1 plus 2 cubed, which will be square root of, that's 1 plus 8, which is square root of 9, which is 3. Then down here we get 1 plus 3 cubed, which will be square root of 3 cubed is 27, so that'll be square root of 28. Square root of 28, square root of 4 times square root of 7, which will be 2 square roots of 7. So we found those first two. Next we want to say, well, what about just a of 2? Well, we're going to use the area function that they gave us. We're going to plug 2 in for the x up at the top. So we have the integral from 2 up to 2 of square root of 1 plus t cubed dt. And we'll note, since the lower limit and the upper limit are the same, this is going to give me back 0. So when we took the derivative of the integral We got the integrand back with x replacing its variable, t. And then to find a2 and a3, we just plug 2 and 3 into that. Or sorry, we find a prime of 2 and a prime of 3. We plug 2 and 3 into a prime's equation. When they wanted just regular a of 2, we had to go back to the regular a formula and let x be 2. And then we were able to solve that out. And we actually didn't have to even do a calculation because the lower limit and upper limit were the same. Okay, this is going to be example 4 from, which is the last example. Put a star on this. This turns up on multiple choice part of the AP test, and just turns up on the AP test somewhat. So this type of problem is one that's good to know for the AP test. So they want us to find the derivative. Find the derivative of, and they give us this function g of x, which is very closely related to an area function. So it's negative 2 up to x squared sine of t dt. So if this integral here, if the upper limit was just an x, then we would be able to, if that was just an x, integral from negative 2 up to x, then we would just be able to take d dx of the equation. We could use our fundamental theorem of calculus part 2 here, and it would just get the integrand replacing with x. The problem is we have an x squared instead of an x. So what I need to do is I'm going to set this up as a slightly different expression. We're going to say g of x, this is an area function, but instead of evaluated at x, it's an area function evaluated at x squared. So basically, because your regular area function would be negative 2 up to x sine of t dt, and then we let the x squared replace the x. So they want us to find the derivative of g, so they want us to find g prime of x. So the chain rule is going to apply here. This will be a prime of x squared. Then we have to multiply it by the inner derivative, which is 2x. So when you all want to figure out what is a prime of x squared, the a prime function, if we took the derivative of an area function, that would just give us sine of x back. But instead of getting back just sine of x, we want the area function evaluated at, or the derivative of the area function evaluated at x squared. So we would get back sine of x squared, and then it's multiplied by the inner derivative 2x. So our derivative of the g function is 2x sine of x squared. So basically you have to note for this, if you have a function that looks like an area function but the upper limit is different, you have to rewrite it in terms of an area function. You take the derivative of the, use the chain rule, take the derivative of the area function, leave the inner part alone, multiply by the inner derivative of your function there. And then to get a prime, you're going to use this statement here. When you take the derivative of this type of function, you get the f of x back. So, but instead of getting f of x, we get a prime of x squared, so you have to replace the t with an x squared, and you have the inner derivative part. I'm going to work one of the problems from our I guess homework stuff that has kind of a similar type one of these. So this will be number 31. Wants us to figure out what's DDS of the integral of negative 6 up to cosine of s, all that multiplied, or that's evaluated at u to the 4th du for the integral. So on the derivative with respect to s of negative 6 up to cosine of s of u to the 4th du. Okay, so this right here, if we kind of call this g of x. This is closely related to an area function. G of x, sorry, our variable is s this time, not x. So we could call this g of s. So g of s, this would equal the area function evaluated at cosine of s. So g of s is this regular formula here that you're trying to take the derivative of. So the area function is, this would be a regular area function evaluated at cosine of s. So if we wanted to do g prime of s, this would equal, we take the derivative of the area function, except instead of evaluating it at s, we evaluate it at cosine of s, and then we have to multiply it by the derivative of cosine because of the inner derivative from the chain rule, which is negative sine of s. So to do this, a prime will be x to the fourth. That'll be the derivative of the area function. You'll just get x to the fourth back. But we have to replace that x to the fourth. We have to replace the x with cosine of s. So we get cosine of s to the fourth power. It's being multiplied by negative sine of s. So if we write it up a little bit cleaner, we would get g prime of s will equal negative cosine to the fourth of s sine of s. And let's check that. That's 31. Let's check that against the back of the book and make sure that that's matching up with everything and I didn't make a dumb mistake somewhere. You can check your answer against, if you know what the answer is supposed to be, it's always a good idea to kind of check it and make sure that everything's working out the way you expect it to. So that was 31. We get negative cosine to the fourth of s, sine of s. So that's what the book says. So that's what we expected to have happen. So everything's working nicely here. So that's basically the process you do these. You rewrite the function as an area function with whatever is up there instead of just the s or just a variable by itself. You put whatever the, whether it's s squared or s cubed or cosine of s, you put that in there. The chain rule applies. And then when you go to take the a prime, you just get the integrand back. But you're going to have to replace the integrand's variable with what's in parentheses here, in this case cosine of s. So instead of u to the fourth, we get cosine of s to the fourth, and then it's times the inner derivative. So we'll stop, that's the book section of this. That should be enough to get started on the 5-4 homework, and we'll record some of the AP problems based around this stuff in a little while.